Okay, children. So in the last class, we had discussed about electrolytic cells and electrolysis, including Faraday's law of electrolysis, Faraday's laws of electrolysis, right? Punya, you just asked me about that physical state of that equation, right? No need to mention aqueous state there. Okay, only need to write sodium plus electron, Na plus 1 electron gives sodium. That's enough. Okay, no need to mention aqueous state. You are right. Okay, then so tell me, which are the two laws of this Michael Faraday according to this electrolysis? Rijas, can you tell me the first law? Yes.
The amount of any substance liberated or deposited at an electrode is directly proportional to the quantity of electricity passing through
Pass
the
through an
electrolyte.
electrolyte. Okay. Mehak, it's okay. Then what about Faraday's second law? Sania, can you tell me? Not audible. No dear. Naurin, can you tell me?
The amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution is proportional to their chemical equivalent weight.
Okay, chemical equivalent weight. Then we have discussed about the products of electrolysis, right? First we just find out the metal that is deposited at anode and cathode in the case of molten sodium chloride, right? Then now we are going to learn about the products of electrolysis in the case of aqueous sodium chloride. Aqueous means that is dissolved in water. Okay. Okay, before that, can you tell me which are the ions present in this aqueous sodium chloride? Which are the ions present in this aqueous sodium chloride? Yes? Anyone? Aqueous sodium chloride. Which are the ions present? Vidur, can you tell me? Yes? Which are the ions present here?
Sodium ions and chloride.
Yeah, Na plus ions. Then chloride ions. It is dissolved in water. So surely H plus ions and OH minus ions are there. Okay. So there are mainly 4 types of ions. From the sodium chloride, it is Na plus and Cl minus. Along with that, water is there, so H plus ions and OH minus ions. So in the case of cathode, okay, in the case of cathode, there will be possibility of 2 reactions, okay, 2 possible reactions here. It is Na plus, it is in aqueous state, plus electron gives Na, sodium. Okay, this is one reaction, and its electrode potential, standard electrode potential, that is equal to minus 2.71 volt. Okay, minus 2.71 volt. And the another one, that is H plus electron. That, yes.
What is the symbol after E?
E cell. This one?
Something like a set. Is it equal to?
Yes, it's equal to. Sorry. Okay, and here it is H plus electron. It gives half H2. It is in gaseous state. And can you tell me the standard electrode potential of this reaction? About hydrogen. What about its value? We have learned it in the case of standard hydrogen electrode. Riya, can you tell me?
1.1.
That is in the case of Daniel cell, right? In the case of hydrogen, we have learned that its value is arbitrarily fixed as
0.
Yes, it is 0. Okay, so it's 0 volt. So there are two possibilities of this reaction in cathode. And we have learned that the standard electrode potential with greater value, okay, with greater value that will take place in cathode. Okay, that means reduction reaction take place with the standard electrode potential with a higher value. So here which one can be preferred? Na++ electron gives sodium, or H++ electron gives half H2. Reduction reaction usually take place with the elements with high standard electrode potential. So in the case of these two reactions, which one has more standard electrode potential? Tell me. You can just look at this value and tell me. Anna, which one has more standard electrode potential here? Sodium or hydrogen? Look at the sign. It is minus 2.71 volt. Here it is 0. Which one is greater? Tell me.
Hydrogen.
Yes?
Hydrogen.
Yes, hydrogen. So this one is preferred. Okay. And we learned that this H+, it is produced from H2O, right? H2O, it is dissociated to form H+ ions and OH- ions. H+ ions and OH- ions. So you have to consider these two equations. H++ electron gives half H2 and these two reactions in the case of cathode. So we can write these two reactions together. H++ electron gives half H2 gram. Okay. So these two reactions can be take place in cathode. Then what about the sum of these two reactions? We can cancel the same terms. Then you can write the final chemical reaction. Which all terms cancel here? From this side, it is H2O plus H plus electron. That's from the reactant side, right? Then in the product side, H plus, then OH minus plus half H2. We can cancel both this H plus ions. Then the final equation becomes H2O plus electron, it gives half H2 plus OH minus. Okay, so this is the final chemical reaction that takes place in cathode. In the case of molten sodium chloride, simply the sodium ions are deposited in cathode, but in the case of aqueous sodium chloride, there are more ions other than the sodium and chlorine, that is H plus ions and OH minus ions. So we have to consider this H plus ions and OH minus ions. And in the case of cathode, the reduction potential, that means higher reduction potential value, they have the more possibility for the reduction reaction to take place. So in the case of sodium ions and hydrogen ions, the hydrogen ions have higher standard electrode potential. So we are considering these two reactions, and we know that hydrogen, it is dissociated to form H plus ions and OH minus ions. Then this is the final chemical reaction take place there in cathode. Is this clear? Yes or no? Sharon, is this clear?
Yes, ma'am.
Gauri?
Ma'am,
Yes.
why
Any
are we
doubt?
preferring the H plus instead of the other one in plus?
Sodium, right?
Yes, ma'am.
Because I told you, in the case of reduction reaction, we are preferring for higher standard electrode potential. So compared to the values of sodium and hydrogen, hydrogen has more standard electrode potential. So we are preferring hydrogen. Clear?
Yes, ma'am.
Okay. So that's about the reaction take place in cathode. Have you completed this one? All of you? Shall I move to next one? Achyut finished?
Yes, ma'am.
Yes. Then Gauri, what about you? Finished?
Yes, ma'am.
Okay. Then the next one is anode. In the case of anode also, there are two possible reactions. Okay. First one, chlorine. Here it is oxidation. So, Cl minus ions, it becomes half Cl2 plus electron. Then one more reaction take place there. That is in the case of H2O. 2H2O, it is dissociated to O2 plus 4H plus 4 electron. These two chemical reactions are take place in the case of aqueous sodium chloride. And here also we can write the standard electrode potentials. Here it is 1.36 volt and here it is 1.23 volt. Okay. These are the two possible reactions take place in anode in the case of aqueous sodium chloride. That means dissolved sodium chloride. Then in the case of anode, the more chances for the reaction to occur with lower standard electrode potential. Okay, lower standard electrode potential. In the case of cathode, it is higher standard electrode potential. Here it is lower standard electrode potential. So can you tell me among these two, which one will happen? It is chlorine or the second one? First reaction or the second reaction? Anode usually prefers the elements with lower standard electrode potentials. Yes, tell me. Yes, Anna, you can tell me. Okay, second one, right?
Yeah.
Yes. Here also the preference goes to second one. But here, you can write here according to this rule, we are preferring second one. Goes to the second reaction. Okay. But due to the over potential of oxygen, okay, in the second reaction, there is over potential of oxygen is here. So we are choosing this reaction. Over potential of oxygen, that means it has more potential difference between those compounds and it will destroy that process, electrolysis. That's why we are preferring this first reaction. Okay. Due to over potential of oxygen. That's the reason. Oxygen, the first reaction that will take place. So in the case of this oxygen, we need to apply this over potential, and there are chances for the electrolysis, it's very less. That's why we are preferring this reaction. So in the case of cathode, it is the reduction reaction that is take place in hydrogen, and here it is in anode. The oxidation reaction take place in chlorine. So these are the two products of electrolysis. In the case of aqueous sodium chloride, that's the difference between the molten sodium chloride and aqueous sodium chloride. Sorry, have you finished the last slide? All of you? Yes, right? Okay. Is this image clear for you?
Yes, ma'am.
Okay. So when concentrated aqueous solution of sodium chloride is electrolyzed, Cl2 is liberated at anode, but at cathode H2 is liberated instead of sodium deposition due to the high reduction potential of hydrogen. Then these are the final reactions take place in both anode and cathode. Okay. This is the just dissociation of sodium chloride in the presence of water. This is the chemical reaction that is take place in anode. That is the oxidation of chlorine. That means chlorine is liberated at anode. Anode. And in the next one, it is in cathode. The reduction reaction take place. The H2 is liberated at cathode. So the net reaction, you can write this one. NaCl plus H2O gives Na plus plus. You can write the final products from this, both anode reaction and cathode reaction, oxidation reaction and reduction reaction. Na plus plus OH minus plus half H2 plus half Cl2. This is the sum of all these reactions, all these three reactions. First the dissociation of sodium chloride into sodium and chlorine. Then the oxidation reaction take place in anode. Second one, reduction reaction take place in cathode. Then the net reaction is, we can cancel the similar terms from both sides. Then final reaction, sodium chloride plus H2O. It gives Na plus plus OH minus plus half H2 plus half Cl2. Okay, so this hydrogen, it is deposited at cathode, and this chlorine, it is liberated at anode. Finished. Finished, right?
Yes.
Anyone else remaining? No one. Okay, then we are moving to the next topic, Do you have any doubt in this one? Products of electrolysis? Anyone? Nothing, right? Okay, then we are moving to the next topic, that is batteries or cells. Okay, batteries, or also it is known as cell. A battery or cell that we used as a source of electrical energy. Okay, it is used as a source of electrical energy. It is basically a galvanic cell because the chemical energy is converted to electrical energy, right? And this battery is also, this chemical energy, it is converted to electrical energy. So we can consider it as a galvanic cell. In the case of galvanic cell also, similar reaction take place, right? The reaction, chemical reaction take place between the zinc and chlorine. It will produce electrical energy. So here also, a battery or cell that we used as a source of electrical energy, it is basically a galvanic cell wall. The chemical energy of the redox reaction converted into electrical energy. So this battery can be also considered as an electrochemical cell or galvanic cell, because here also chemical energy, it is converted to the form of electrical energy. And there are two types of batteries, mainly two types of batteries here: primary batteries and secondary batteries. Primary batteries and secondary batteries. We can classify these batteries into primary and secondary. Do you know on what criteria we are classifying this one to primary and secondary? Yes. What's the difference between the phone battery and the batteries that we used in clocks? In phone battery is there, then in clocks, watches, etc. there is some battery there, right? Right? Well, then what's the difference between these two? Yes, Punya?
Reusable.
Yes, reusable or rechargeable, right? So, based on this criteria, we are classifying this one to primary batteries and secondary batteries. This one is rechargeable or reusable. Okay, shall I move to next one? Yes, right? Then we are going to learn about primary batteries. Okay, primary batteries. Here the reaction occurs only once, and after use over a period of time, battery becomes dead and cannot be reused again. Okay, that's a feature of this primary batteries. The reaction occurs only once, and after use over a period of time, battery is dead and cannot be reused again. Example for this type of battery, it is Leclanche cell, or it is otherwise known as dry cell, that we used in clocks, transistors, etc. The first one. Okay, this one is dry cell or Leclanche cell. Then the second one is mercury cell. It is used in hearing aids, watches, etc. This one is mercury cell. So the primary batteries in which the reaction occurs only once, and after use over a period of time, this battery becomes dead and we cannot reuse again. Examples for this type of primary batteries, first one is Leclanche cell, or otherwise it is known as dry cell. Then the second one is mercury cell. It is used in hearing aids, watches, etc. Aditya, can you read the slide about primary batteries?
Yes, ma'am.
Okay.
Primary batteries. The reaction occurs only once, and after use over a period of time, Battery becomes dead and cannot be reused again.
Okay.
Example, dry cell. And that is
Leclanche cell or dry cell.
Leclanche cell or dry cell. It is used in clocks and transistors.
Okay.
Then mercury cells. It is used in hearing aids, watches, etc.
Okay. Have we completed this one? Yes. Then we can learn more detail about this two types of cells. Not two types of cell. From this primary battery itself, two examples here. We can learn detail about this Leclanche cell and mercury cell. So the first one, it is dry cell, or otherwise it is known as Leclanche cell. Okay. Okay. So in this type of cell, this anode is zinc container. You can look at this image. Here you can see that anode as a zinc inner case. Okay. We are using this zinc container as an anode, and at the middle portion you can see one graphite rod. Here it is act as a cathode. Okay. The carbon, that is graphite rod, it is surrounded by powdered manganese oxide and carbon. Okay, powdered manganese oxide and carbon. So here the anode, it is the zinc container, and the cathode, it is carbon, that is graphite rod. Graphite, that is made up of carbon, right? This graphite is the allotrope of carbon. So the cathode, here it is graphite rod, it is surrounded by powdered manganese oxide and carbon. And we know that in this galvanic cell, some electrolyte is needed, right? Some electrolyte is needed, and here as an electrolyte we are using moist paste of ammonium chloride and zinc chloride. Okay, moist paste of ammonium chloride and zinc chloride. So there is one zinc inner case. Inside that, at the middle portion, there is one cathode. It is made by graphite, and it is surrounded by the powdered manganese oxide and carbon. Okay, along with that there are certain electrolytes. It is ammonium chloride and zinc chloride. Here also you can write zinc chloride. Okay, so the electrolyte, it is the moist paste of ammonium chloride and zinc chloride. Then the electrode reactions take place in both anode and cathode. In anode, zinc, it is oxidized to Zn2 plus 2 electron. Okay, here the anode is zinc and it is oxidized to Zn2 plus. Zinc gives Zn2 plus 2 electron, and in the case of cathode, MnO2, manganese oxide, ammonium, they react together and gains 1 electron to form this MnO, that is manganese oxide, then OH. It will be known as manganese oxide hydroxide. Manganese oxide, then in bracket you write hydroxide. Okay, manganese oxide, hydroxide and ammonia. So this is the reaction that takes place in cathode. The powdered manganese oxide, it reacts with ammonium and gains 1 electron to form manganese oxide hydroxide and ammonia. And in this cathode, this manganese, it is in +2 oxidation state. We have learned about oxidation states, right? How can we determine the oxidation state of an unknown element? In the case of this MnO2, right? MnO2, sorry, here it is +4. It is +4. Okay. In the case of MnO2, you know the oxidation state of oxygen. It is always -2, right? It is always -2. The oxidation state of oxygen, it is always -2. And here it is 2 oxygen atoms. In manganese oxide, there are 2 oxygen atoms. So it becomes -4. So 2 into -2, it is -4. sum of this oxidation state of a compound, it is always 0. Okay. So the oxidation state of manganese, it is +4 in this manganese dioxide. This is the method to find out the oxidation state of unknown element. Okay, in the case of oxygen, its oxidation state is -2, and here there are 2 oxygen atoms. So 2 into -2, it is -4. Then the oxidation state of a compound, it is 0. So in order to make 0, we will put +4. So +4 plus -4, that is equal to 0. So the oxidation state of manganese, it is +4. So here it is +4, and in the case of MnOOH, here it is +3. Okay. So the that means the oxidation state reduces, right? That means reduction reaction take place here. Okay, then here one product that is formed is ammonia, right? This ammonia, it will react with, yes,
oxidation state of oxygen is -2.
yes, dear.
The oxidation state of oxygen is -2.
Yes, yes.
So -2 into -2, it should be +4.
-2 into 2. Okay, only 2. Okay, then it becomes -4. Then here +4. Clear? Okay. Then this ammonia, it reacts with zinc ions to form a, here zinc ions are formed, right? This ammonia, it reacts with zinc ions to form a complex. It is ZnNH3 4 2+. Here one complex is also formed. This ammonia that formed in the cathode reaction react with the zinc that is formed in anode reaction to form a complex. It is ZnNH3 4 times then 2+. Okay, its charge is 2+. And here the dry cell has a potential of nearly 1.5 volt. The potential difference of this dry cell, it is 1.5 volt.
Ma'am,
Yes, Achyut?
when the battery or cell leaks, is it the electrolyte that is coming out?
Not clear once again?
And when the battery or a cell leaks, the electrolyte that is coming outside.
Yes, dear. That's in the powdered or moist form, right? This electrolyte, it comes outside. Okay. So is this clear for you? In the case of dry cell or Leclanché cell, anode, it is the zinc container. Okay. The zinc inner case that is made up of, this zinc, it is act as an anode. And here it is the cathode, that is carbon graphite rod at the middle. It is surrounded by powdered manganese oxide and carbon. Then the electrolyte, it is the moist paste of ammonium chloride and zinc chloride. Then the electrode reactions are, in the case of anode, zinc is oxidized to Zn2+, and in the case of cathode, manganese oxide reacts with ammonium ions and accept one electron to form manganese oxide hydroxide and ammonia. This ammonia reacts with the zinc ions to form zinc ammonia complex, that is ZnNH3 2+. And the dry cell has a potential of nearly 1.5 volt. The potential difference created in this dry cell, it is 1.5 volt. This is clear?
Ma'am,
Yes.
why is the powdered manganese not getting mixed with the paste?
Here it is used as a catalyst, or to make the surface area more, to make the reaction faster. Okay, and it is reacted together with this carbon. Okay, Steffi, your question, why this manganese oxide?
It's powdered form, right? So why is it not mixed with the electrolyte when it is placed together?
Here in the outside of this graphite rod, it's already mixed. That's why this reaction take place. Manganese oxide, it is reactive with NH4+. Okay. Okay. This is clear?
Okay. Yes,
okay. Then shall we move to next one? Next type of this primary battery. Yes or no? Just tell me. This is clear.
Yes, ma'am.
Okay. Then the next one is mercury cell that we used in certain watches, etc. Okay. Here the anode is same zinc amalgam. Zinc amalgam means zinc is mixed with mercury. Okay. Hg, that is mercury. That is zinc amalgam. And the cathode, it is a paste of mercuric oxide and carbon. This portion is anode. Okay, this one is anode. Then here it is anode cap. That's clearly in your textbook. Okay. Then this is one gasket. Separator. This one is cathode. Cell can. This is the structure of this mercury cell. Just 1 minute. Okay, children. So in the case of this mercury cell, this anode, it is zinc amalgam. That is the mixture of or the combination of this zinc and mercury. Then the cathode, it is the paste of mercuric oxide and carbon. And here the electrolyte, it is the paste of potassium hydroxide and zinc oxide. Then the electrode reactions take place here. In the case of anode, the zinc amalgam, it will receives OH minus ions and it becomes zinc oxide. Okay, plus H2O plus 2 electron. How this can be identified as an oxidation reaction? Can you tell me how can be this reaction is considered as an oxidation reaction? We learned that the losing of electrons, it is considered as oxidation. Then addition of hydrogen ions, losing of hydrogen ions is considered as oxidation. Then addition of oxygen ions, it is considered as an oxidation, right? Here this zinc receives oxygen ions. That's why this reaction becomes oxidation reaction. Okay. And in the cathode, this mercuric oxide, it reacts with water and receives electron to form mercury. Here this oxygen, it is lost, right? Oxygen is lost by this mercuric oxide and it becomes mercury. So it is considered as a reduction reaction. In the first case, zinc amalgam, that means zinc, it receives or it gains one oxygen and it becomes zinc oxide. That's why it belongs to the category of oxidation. And in the second reaction, this mercuric oxide, it just lost one electron and it will become mercury. That's why it is considered as reduction reaction. Then we can write the overall reaction. We can cancel the similar terms. Then it becomes zinc amalgam plus mercuric oxide gives zinc oxide plus mercury. Zinc oxide plus mercury. And here the cell potential, it is 1.35 volt. 1.35 volt. Do you know what you mean by this gasket? Anyone? Gasket. It is actually a seal that is used to prevent the leakage. Okay, this used as a seal between two layers and it prevents the leakage of the substances. Clear? Then the separator, it is used to separate this anode and cathode. So these two cells are the examples of primary batteries. First one is Leclanche cell or dry cell, and the second one is mercury cell. In both these cases, we cannot reuse it again, because once the chemical reaction has taken place, and after a period of time, this battery becomes dead and we cannot able to reuse it. Is this clear? All of you? Yes, right?
Yes.
Yes. All of you, please switch on your videos.
Can you show that slide?
Yes, sure. Manual finished? Yes, right? Okay.
Yes, ma'am.
Okay. So, Nia, please switch on. Which are the two types of batteries that we have learned? Nia, are you there? Okay, fine. Shivani, can you tell me? Yes, primary batteries and secondary batteries. What do you mean by this battery? Aditya?
And this is used to provide a source of electrical energy.
Yes. So what energy conversion take place there?
Chemical to electrical.
Yes, chemical energy is converted to electrical energy, similar to that of galvanic cell. And what do you mean by this primary battery, Gayatri?
Reaction only happens once, and after the reaction they'll be dead. Batteries.
Yes, we cannot able to reuse it again. Which are the two examples for this primary battery? Krishna, can you tell me examples for this primary battery?
Mercury cell.
Yes,
Cell.
mercury cell and dry cell. What's the other name of this dry cell, Srihari?
Leclanche cell.
Yes, Leclanche cell. Then which are the anode, cathode and the electrolyte that is used in this dry cell? Steffi, can you tell me? You can refer the notes. Then tell me.
Anode is the zinc container.
Anode is zinc container, okay.
Cathode is the carbon graphite.
It is surrounded by, you can also write that one, okay. It is surrounded by, tell me.
Manganese oxide and powdered manganese oxide.
Then?
And the electrolyte is a moist paste of zinc chloride and NH4Cl.
Okay, ammonium chloride.
Ammonium.
Okay, then what about the potential difference or the cell potential of this Leclanche cell, Rijas?
1.5 volt.
1.5 volt. Okay, then what about the cell potential of this mercury cell, Achyut?
1.37.
Yes, it is 1.35 volt. Then what about the anode, cathode and the electrolyte in this mercury cell? Punya?
Zinc.
Yeah, zinc is the anode, zinc amalgam is the anode. Then
Sulfuric oxide is water.
Okay, then what about electrolyte?
Paste of potassium hydroxide and zinc oxide.
Okay, fine. Then we can just write what do you mean by this secondary batteries. Okay, you can write down secondary batteries. It is the cells which can be recharged by passing current through them in the opposite direction so they can be used again. Okay, cells which can be recharged by passing current through them in the opposite direction so that they can be reused it again. The class is still 11:50, right?
Yes, ma'am.
Okay, now it's 11:54. We can continue this topic in the next class. Okay, just wait. Let me take your attendance. Okay, children. So thank you all. See you in the next class. Okay, bye.
Thank you, ma'am.
Thank you.